Hello guys, welcome to this new video. So we are now going to go through question 4 in the May 22 Time Zone 2 paper 2. So the first question is about Kirchhoff's laws. In the new syllabus we do not need to learn this anymore, so we will skip straight to part B. So in part B we are told that a cell is connected to an ideal voltmeter and a switch S and a resistor R. The resistance of R is 4 ohms. And when this switch is open, so in this state, the reading is 12 volts. And when we close the switch, we read 8 volts. So firstly, we need to state the EMF of the cell. And for that, we need to know the definition of the EMF, or how we can measure the EMF. And well, simply put, the EMF can be measured when the current through the cell is equal to 0. Current through cell is 0. So this is the definition of the EMF. That's how we can measure it. So when zero current is flowing through the cell and we measure the potential across the cell, we will measure the EMF. And well, when the switch S is open, we're going to have no current flowing in this way, as the circuit is broken, so there's no way for current to flow in this space here. So we're only going to have this as the circuit, and since the voltmeter is ideal, it has infinite resistance, so there will be no current flowing through the battery, and when that is the case, we measure 12 volts. And so the EMF will just be 12 volts. And then we need to deduce the internal resistance of the cell. So we know that when we close the switch, so when current is able to flow this way as well, then this voltmeter measures 8 volts. And well, this voltmeter is connected across our resistance R. So this voltmeter measures the potential drop across our resistance R. It's connected to the two sides of R, and we know that it measures 8 volts. So that means we have 8 volts across our resistance R. Now from this we can use V is equal to IR to calculate the current in R. So the current will just be V over R, which is going to be 8 over 4, so 2 amps. And well, if we know the current flowing in the cell, then we can just use the formula that connects the EMF and the internal resistance. So the formula that we can see in our data booklet is that EMF is equal to I times big R plus small r. So from this we pretty much know everything except for small r. So we know that our EMF is 12, our current is 2, our resistance is 4 plus our small r. And well, if we do this, then we will see that the small r, the internal resistance, has to be 2 ohms for this equation to work. So yes, this can also be thought of by the fact that the battery itself can supply 12 volts, but it has to supply some energy to push current through its own internal resistance. And well, if we have 8 volts being used up by the resistor, that means the remaining 4 volts will be used up by our internal resistance. And from this, when we calculated that the current is 2 amps, we know that 2 amps flow through our internal resistance. And so we can again use V is equal to IR to see that if we have 4 volts and 2 amps across something, then the resistance must be 2 ohms. And well, this is pretty much the same as this formula. It's just a different way to see it, maybe an easier way to remember. And well, this question is also from the old syllabus. Again, it's related to Kirchhoff's laws, and so is the second part. So we will skip to part D. So we are told that electricity can be generated using renewable resources, and we need to outline why it's a secondary energy source. Well, a secondary energy source is just one that is produced using other sources of energy. So it also states in the question that the electricity is generated by using other sources, and therefore it's a secondary source. So electricity is generated, and we require other forms of energy to produce it. Then we need to outline what is meant by a renewable resource. Well, simply put, that a renewable resource can be replenished faster than is being used up. Replenished faster than it is being used. So for example, the sun is producing energy at a faster rate than we're able to harvest it. So every time we take a bit of energy, there's plenty more in a reserve, so it's never going to really run out. And then it's part E. This one's a little bit of a lengthy question. So we are told that a fully charged cell has an EMF of 6 volts and it runs for a current of 5 amps for a time of, well, a fourth of an hour until it's completely discharged. And then this cell is recharged with a rectangular solar panel, and we are told the intensity on the solar panel. And we also know that the efficiency of our solar panel is 18%, and we need to calculate the minimum time required to recharge the cell fully. So let's just say that we have our cell over here, and when we are discharging it, we are taking out energy from the cell. So some energy comes out, and if we want to recharge it, then we will have to supply from a different place some energy to recharge it. So what I'm trying to say here is that the energy that comes out of the cell must be equal to the energy that comes into the cell. And these two things we can both calculate. So we can calculate the energy that is going out of the cell, as we can calculate the power from simple circuit formulas. So we know that power is just voltage times current. So we know the EMF and the current across through the cell. And we also know that power is equal to energy over time. So that's just how much energy it uses per second, let's say. So from this, we see that the energy will be the power times this time. So if we calculate this will be 30 watts. And from this, we can calculate, so this just means that we use 130 joules every second. Alternate units for this are just joules per second. But we don't only operate it for 1 hour, for 1 second, we operate it for 0.25 hours. So we need to convert this into seconds, and so we can do that. So energy is power times time. So 30, we need to convert it into seconds. Well, 0.25 times 60, this many minutes, times another 60 for this many seconds. And so this will be 27,000 joules. So we need to supply an equal amount of energy into the cell if we want to recharge it fully. So let's see how much energy the solar panel provides our battery per second. So we know that the incident power, or the incident intensity on the solar panel is 380 watts per meter squared. So for every square meter, we get 380 watts. But we don't have a square meter, we only have this rectangular area of 0.4 times 0.15. So we can calculate the solar panel, how much power we get from it. We can just multiply this 380 by the dimensions of our solar panel itself, so we get how much power it produces, like this. And well, we also know that the efficiency is 0.18. So this is how much power it would produce if it would be 100% efficient. But it only makes a small fraction of this because it loses some energy. And this ratio, this factor, it decreases by 0.18. So if you want to calculate the useful power that we actually make, we actually have to multiply this by another 0.18. And well, if we do this, we get 4.1 watts. So we need to see how much time we need to operate this solar panel, which makes us 4.1 watts to get the same amount of energy that we got out of the battery. So we can say that we need to run this for some time t, with the same concept that this will be the energy from the cell. So energy of cell. So that this will just be the power times the time. That's the same calculation we did over here. And we know that this has to be equal to the energy that we got out, so 27,000. And well, from this, we will see that the time is going to be approximately 6,600 seconds. So this is the minimum time. And then finally, we need to outline why research into solar technology is important. And well, there are many possibilities here. Almost anything you can think of that's related will probably be correct. But one of these is that solar is renewable. And so this will help reduce greenhouse gases. Yes. So this was the end of question 4. I hope I was able to help answering this question, and see you in the next video.